Alright, so today I wanted to talk about equations of shapes, trigonometric identities, and a little bit about the unit circle. I didn't really find the unit circle to be that complicated. Alright, so when the unit circle was designed, it actually had a 360-degree system, which is pretty evident right now if you took, I don't know when you learned it, but, we decided to change that because it was in base 60 and it didn't really make much sense to use that system because I'm pretty sure it was based on the solstices or whatever you call it, but I'm not too sure. So let's just start talking. Let's just bring up a basic square. So if you were to find the area or the perimeter, obviously you can just add up all these. You get P equals 4S, and let's see, you have an array. Array is just a set of numbers that are in rows and columns. So you can just do this. Consider only 1, then it's 1 by 1, and that'll become just basically an area of 1. So you have A equals S squared. Though, here's some stuff. Well, not some stuff. It's weird. Words are funky. So, the way you can think about it is that this is just a special case for a rectangle. A rectangle can't be a square because a square is always set like this. A rectangle is a lot more dynamic. You can stretch out this part, you can make this larger, it doesn't matter. All we know is that it's a special case for this. I think it's called a subset. I'm pretty sure even a parallelogram should be considered a rectangle. Actually, a rectangle should be a subset of a parallelogram, if I were to be certain about that. I don't know, I haven't looked at it in a while. But here's the thing. Let's say if we split this in half, and you get, your root 2, using the Pythagorean Theorem. But how is this area found? Well, it's really simple, because if you think about it, the triangle is just half this area. Here, let's just back it up. The triangle formula can really be found based off of comparing it to a rectangle. Because think about it this way, if you were to have an array of like 3 by 2, wow, that's a crappy square. Kind of looks like Ninja Turtle abs. So if you created this array and you started multiplying it, 3, 2, and your basic area is just base times height. Or should just be called length times width. So what would be the triangle of this? Well, think about it this way. If you get a rectangle from length times width, then can't we just do this? It's a triangle. This would have the same area as that triangle. Splitting it down the middle, right over here, any way that's actually diagonal, that creates the triangle. So we can go off of this. We can consider length times width. And since we have a special case for square, I don't know, just make it equal to any one of these variables, it doesn't matter. So it's A equals L squared. And now that we know that triangle, we can just go off of A equals half. I don't know, we probably shouldn't use the same variable, otherwise it doesn't make any sense. Let's call this AS and AT, because that means turtle. That was kind of stupid. But, so we have an area of a triangle, area of a square. We can just multiply this by 2 on both sides. And since you can just add up the areas to create the square, this should prove that it makes up the square, proving the formula of a triangle. Although, I don't know, I haven't done proofs in a little bit. But it does make sense to have that because it does compose the triangle. You can make the same reasoning for a rectangle, it doesn't matter. All I know is that the area of a triangle works with arbitrary values. Alright, well, enough with that. I said I wasn't going to do these proofs. I don't know why I keep doing that. Alright. See, what was I going to talk about? Alright, I'm not going to prove Heron's formula. I'm just going to write it down and talk about what you're going to do. Oh, my board's dirty. Alright, let's consider this triangle right here. See, A, B, C. 1, 2, 3. Okay, so you have the perimeter, P, equals A plus B plus C over 2. There. So if you were to have values, you just correspond it into each one of these. I should probably talk about how a triangle is actually composed of. Because each side, when you add it together, it should be bigger than this side. If it isn't, it's not a triangle. And that's for any case with the triangle, because it wouldn't reach this side. You can use a measure stick. It will work. So, you should probably follow this. B plus C must be greater than A. C plus A must be greater than B. And then A plus B must be greater than C. Alright. So now let's just keep continuing with this formula. Just remember, these are the requirements for a triangle to actually exist as a triangle. Otherwise, it's just a line that's kind of broken. Now let's talk about the area. So the area goes as follows. Let's see, this is how you spell Heron. A equals the square root of S minus A, S minus B. Oh, this is coming out stupid. Ugh. Wait, why did I use S? And obviously you could just keep plugging these into here and you can satisfy this pretty well. If you want to do this with basic arbitrary values, go right ahead. It doesn't matter to me. I mean, if you want to prove it, that's fine. It's just that it's already been proved, so there's really no point of doing it. But he found this based off of the fact that it wasn't a right triangle. I believe this is a special case for an isosceles triangle. Yeah. And, which comes out to be the equilateral triangle. Is there really much else to say about this? Not really. It's just that it's a lot more different if you base it off right triangles, which is the 90-degree angle right here. That's not my marker. Because it composes of the square and the rectangle, or the square-tangle. Alright, now let's start talking about trigonometric identities. So, First of all, these are notations. These were not really called sine, cosine, tangent at the time when the Egyptians were using it. But it's all based on this single circle. Alright, so thing cut out while I was talking. So when you're... Oh, but start talking about this. So I was going to originally use the circle, but I'm just going to start with the triangle. Because, well, triangle is the basis of trigonometry. I mean, I'm not going to talk too much about trigonometry. I'll probably bring it up once I get into the more advanced topics, like the different identities. But, alright, so when you're talking about trigonometry, we're going to base it off this. This is always going to be the assumption that I'm talking about when it comes to the unit circle. This is the angle I'm referring to, which makes this the adjacent and this the opposite. Okay, so we'll do it by the basic school notation, OAH. I don't remember what the thing was. It was like I don't know. But, so we have this. We have sine theta, which is normally the notation. Theta, that's just a Greek letter. And that's going to equal... Did I just forget? Oh. O over H cosine theta equals A over H. And tan theta... Let's see, it's sine over cosine over H divided by A over H. The H is canceled because this one goes to the top. So it's going to be opposite over adjacent. There. These are the notations for trigonometry. This is pronounced sine. When you spell it out, it's S-I-N-E. It's not sin, it's sine. Imagine how many people you have to talk about to actually explain it like that. I don't even think if that sentence made any sense. I don't know, it's like 2 in the morning right now. But, this is going to be a cosine. It's co before the sine. This is tangent. T-A-N-G-E-N-T. Just in case if you didn't spell it correctly. I don't know why I spelled that out loud instead of sine, S-I-N-E. I am being weird right now. And we're not talking about like the tangent to... Oh, pop my neck. The tangent to, like, if you start talking about something random, like me accidentally trying to prove something in the middle of a video that claims that he wasn't going to do proofs. But anyway, the idea of a tangent is really like this. When you touch it right here. Now, this is where the circle comes in, because a circle is defined to be x squared plus y squared equals r squared. R squared is going to be the radius squared. And obviously, you can see that this is the Pythagorean Theorem, which is what I've been talking about since the first video I created about this series. So it's a function of a triangle. That's just some funky stuff, dog. So if you were to square root x squared plus y squared and find your radius like that, you can. It's just that you need to find this. And if you need to find the centers, just make r squared equal to 0. Or, I believe that's how you do it. I don't know, I haven't thought about it in a while. Let's see. If you were to change this, x minus 3 plus y plus 2 squared. 3, negative 2. Which means that on a Cartesian coordinate plane, yeah, it should work out like that. Just plug in your zeros for each of them. Now, here's the part where it starts getting a little funky. Because if I remember correctly, with the degree system, we go off of 360. Now we're going to talk about radians. Radians are not very complicated. It's just a new way to think about it because it can compose the entire circle. Alright, so we have our quadrants, 1, 2, 3, 4. If you didn't know that, I'll just put it down right here. And we're going to separate this into the basic 45 degrees all the way around. Alright, now here's how you convert degrees to radians. You have pi over 80, pi over 80. You didn't hear that. I don't know, I don't really write down the conversion factors, I just kind of do them. And we'll just call this D for degrees. And it's normally written as rad. Let's put an equal sign so that it makes sense. Wow, my handwriting is atrocious. And radian is just R-A-D-I-A-N. I don't really have any history about why they did this. It just makes more sense because it composes a circle. But we're going to have to do this. So now 30, 45, 60. Which, if you were to remove the 45, it's just a third. Not a third. What am I talking about? Sorry, sometimes whenever I'm trying to explain stuff, I think about other stuff. That's why I pre-record the stuff, you know? So, if you were to try and convert this back to degrees, all you have to do is follow this simple equation. It's just degrees, which on a calculator you'll see deg. And that's equal to 180 degrees over pi times r, standing for radians, not the radius, the radian. Dang, I wish there was more stuff to talk about, but it just seems so simple the way they got to here. I mean, it took a while to actually discover. Focus. Okay, there we go. One talking to you guys. My marker. Oh, it's in my pocket. Now, let's just talk about this function of x squared plus y squared equals r squared. I accidentally erased that part for some reason. Now, I'm going to use a little idea of limits from, I don't know, this Greek guy. Weird. So, you have a function that's directly related to r. Now, let's just start thinking about it. If we were to compose this quadrant right here, the first quadrant, how many values can you put in there? Well, the funny thing is that you could put in an infinite amount of values. I mean, think about it. This is, if we were to create this, which 0 to 90 degrees, or pi over 2 degrees, not pi over 2 degrees, what? Pi over 2 radians. If we kept plugging it in, and we use this notation of cosine theta, sine theta, to get our coordinates, which, there's a little trick. Hold up, before I start talking about this infinity stuff, just a little touch on calculus and how limits can describe behavior. Just know, when you're talking about the unit circle, you can use this simple trick, because it'll work for any side of this circle. So it goes right here. This is going to be 30 degrees, and then 45 degrees, 60 degrees, and then all the way back over here. So this is our 0, and this is our 90, and then you can just tilt it over here, and you'll get the same value, but you have to remember that we're in the negative x coordinates. Don't just think about it in unit circle, because this still is a Cartesian coordinate plane. It's just that, I don't know, you don't really see it as much. It'll probably pop up in like some trig test or something, and it won't give you that, because that's how you can view it. Because you have a positive y value, negative x value, negative x value, negative y value, and so on. That's why it'll work like that. So just multiply it by 1 every single time, whatever side you're on. That's pretty much the best way I can explain that. But, oh yeah, I forgot to write how the coordinates work. Okay. So if we were to compose this all the way from 0 to 90, then you can plug in any value and it will still compose it as long as it's within that range. So pi 3.1415 something something something, it will infinitely approach that value. But the thing is that even though there's an infinity inside of this circle, it will reach that value because of limits. Like, I can't remember what the thing was. I remember reading about it somewhere. I think it was like 0.999 repeated x. Wait, was it? Actually, no more proofs. Just assume that 0.99 repeated will end up equaling 1. So, oh, I really want to explain that. We'll bring it up back in calculus. If anyone watches this video, remind me to do that. So, let's go back to this. Just think about it. If you're going all the way around this value, you can plug in infinitely many values, like trying to contain God within walls. It just doesn't make any sense. But that's the idea of a bound. It's a bounded function if you can only fit in this circle. It's even more bounded when it's over here. This actually leads to the concept of bigger and smaller infinities, which sounds really contradictive, but it's true. Those have to exist. Like, alright, I'm going to sidetrack a little bit. Just, let's talk about countably infinite. So, countably infinite is like going from 1, 2, 3. And that's how many numbers are within the number 4. But there's still an infinite number of values in that. But what about the countable parts of 1? Well, there aren't really any, unless you count 1. Although there's an infinity within 0 and 1, it's still going to be smaller than 4. And that's the concept of big and small infinities. But I'll talk about more on that once the next video starts up. Alright, so now here is the part that I start talking about the identities. Because I think I talked mostly about this unit circle, and I hope that you understood it. I will literally go back just to explain it again on the littlest topic. All I want you guys to do is just understand this stuff, because it just doesn't seem too hard. But I'm not you. I don't know how you think. Because I've met people that have had problems with addition in, like, what was it, 9th grade? It's kind of stupid. Well, not stupid. Alright, let's just cut over that. Now, here is the Pythagorean identity. Sine squared x plus cosine squared x equals 1. This is one of the most famous identities that we have ever found. Well, not we, that people have ever found in trigonometry. Because if you were to multiply any value you get for sine, along with cosine, of similar triangles. By the way, when I bring up triangles involving the unit circle, this will always be our x, this will always be our y, no matter where it is. If it goes over here, it's still always going to be the x. I will probably not switch between that because I don't care about the other stuff. Because it's really dependent on the angle right here. But any sine or cosine you get, it will end up equaling 1. It's actually quite fascinating. And all you have to do is just divide it by any value that you find. And you'll end up getting it. Well, any oh, why do I keep saying it like that? I forgot what it's called. Trigonometric names you get from this. And that's actually how it was discovered with the other ones. Let's see. Sometimes I don't want to like actually write something wrong, and then you guys learn wrong information. That's not what I intend to do. So we have secant squared theta minus tan squared theta equals 1. That's another identity. And you can get that, I believe, by dividing by cosine squared. If I were to look at this and kind of reverse it. And you can also get another identity, which is cosecant squared minus cotangent squared equals 1. Now you're probably thinking now, why did he mention these identities without explaining what these are? Think of it as, no, not the inverse, that's a completely different thing. The opposite of these, there. Even though I'm pretty sure inverse means opposite. I don't know. So, cosecant means 1 over sine. Okay? And then secant means 1 over cosine. This will be spelled S-E-C-A-N-T. This one is just adding a co before the thing. So we have 1 over cosine theta. Do I even have enough room? Yeah, I think I do. Then we have cotangent, which is going to be cosine theta over sine theta. You'll see more of a reason why these things exist once calculus pops up. But for now, just know that these exist. Actually, it applies to many different things. I just don't want to talk about any of them. And let's start talking about this thing called a terminal angle. I can't wait to wash off this marker board. Oh crap. I'll just admire the dirty whiteboard. Let's say we have 720 degrees. Now, do we have a circle that can fit that? Yes. Think about it. If this is a full rotation around, then this goes around again. It doesn't actually increase like that. I just wanted to explain it like that. Kind of looks like a moon. Well, not our moon. I don't know, maybe if I had fingers. Okay, let's not go off on a tangent. Hey, tangent. So, since we know that 720 degrees is just 2 rotations around, then it's really just 360 degrees. Now you're probably thinking, wait a minute, this doesn't make any sense. Well, you're right, but at the same time, this is based on something called modular arithmetic. It's basically just circular arithmetic. Circular numbers. Like this thing, see, it's called modulo, k, and you'll probably learn this if you take pure mathematics or just something with this. Okay. The thing is cut out 3 times now. I'm having a lot of fun. So let's try and get this done as fast as possible. No, that's not the best graph of that. But let's just continue on. Okay. So, just using the idea of a unit circle, and we call this 0. We'll call this pi over 2, pi, 3 pi over 2, 2 pi. So, what is the cosine of 0? Well, it's actually going to be 1. The reason being is that if you go off a triangle, even though it isn't a triangle, it's actually just a straight line. Cosine of 1 over 1. Cosine of 0 is going to end up being 1 over 1, which is going to be 1. That's why you get the maximum value right here. This one will end up 0 because it's 0 over 1. Even though it's a line, you can still treat it as if it were a triangle. And that's the funky thing about triangles in this case. So, since we can define these to be the cosine graph and the sine graph, then why do I have these dotted lines right here? Well, it's because right here it divides by 0. Now, I'm not sure how old you are. Maybe your elementary school told you that you can divide by 0 and you'll end up with 0. No, that's not true. You don't have an answer. You can try. It will not do anything. This is what we call a vertical asymptote. And this is the tangent graph, sine over cosine. So that's why at pi over 2, just as over here, you end up with an asymptote, because cosine of pi over 2 is 0. And the other graphs, you can do the same reasoning. It will still end up with these vertical asymptotes with those opposite ones. And the thing is that you can trace the graphs along this, because in this quadrant, you actually end up through here. And then over here, you're back down to a negative value, which is completely reasonable right here when you have a -1 for a radius. And then it just goes back. It's modular, so it's going to completely go through infinitely. That's why it's called modular. And I don't think there's anything else I need to talk about, but if I need to explain something better, please tell me. But I guess that's it. I felt like my teaching wasn't too well today. Kind of jittered a little bit. Not sure why. But, God bless you. See you in the next video.